Okay, we're going to try and talk about today two topics, average value of a function and the definite integral in finance. Okay, so I'm going to start with the first. All right, so here's the game. I want you guys to, well, I tell you what, I guess what I didn't do here is I didn't tell you what the function f of x is. But you could draw any function you want. So why don't you draw a graph and draw any function that comes to mind on the graph. And I guess the other thing I didn't do is I didn't tell you what A and B are. So you can put A and B anywhere you want. And then I want you to show me what this integral represents. We know it's area under a curve, right? Or area between a curve and the x-axis. So you could draw some kind of a picture that goes along with that. And then, why don't you write a story? Okay? Because we're supposed to interpret. So you have a picture of a function, and you have some area drawn. And next to it, I want you to write a little story telling me what's going on with the function. And I will read out loud into the microphone for all posterity the best story. Ready? You have, let's say, 1 minute. Shoes being acquired at an exponential rate. We have Lunchables being eaten. And over time, how many you eat. Tough call. I'm going to have to go with the road trip. So everybody likes taking a road trip, all right? And so, yeah, Mike's drawing some kind of function like that. And he drew area from starting at 0, or was it starting?
I mean, it was starting close to 0, but I just kind of...
Somewhere around here?
Yeah.
And somewhere around here? And he said, okay, we're finding this area here from A to B. So now, this is his function f of x. And what's f of x represent? I guess that's the question.
The rate you're going at.
The rate, right? If we have a rate function, or a speed, this is speed in this case, right? Miles per hour. Then when you integrate from A to B, you're finding the total what? The total miles, the total accumulation of the numerator of your rate, right? Total number of miles that he traveled. And he added some. He said that, you know, I forget why you slowed down as a speed trap or whatever it was, but he had something going there. It was a nice story. Okay. So here's your picture. Okay, fine. Here's part B. And actually, you could all try this. Same problem. Can you draw a rectangle, maybe right on your picture, that has the same area as your picture? So if we look at Mike's here, can I draw a rectangle? This shape is not a rectangle, is it? How do you know if you have a rectangle? Yeah, you have to have all the sides. Well, first of all, they have to be lines, and you have to have right angles, right? And I have a linear side here, and I have a linear side here, and I have a linear side here, but unfortunately, I have a curve here, right? So my question is, can you draw a rectangle that would have the same area? Try it on yours. Yeah, I just want to point out another example. I forget who had this, but some people had, you know, like a triangular picture, where maybe A was 0, and B was some number up here. So you have, you know, your function is a line. Here's your g of x, let's say. And so that's the area that you found when you integrated from A to B. Okay, so my question is this. Let's start with the triangle, because that's actually easier. How would you turn that into a rectangle? What would you do? Times it by 2, right? Because we know that the area of a triangle, you have this beautiful formula, which is 1/2 base times height. And we know that the area of a rectangle is, yeah, base times height or length times width. So the area of a rectangle, I guess, is twice as much as the area of a triangle. So What you don't want to do, I guess, is go right here, because this rectangle would have double the area of the triangle, right? So what would you want to do? Go half as high as that, right? Go right here. And if I drew a line right here, right? And then if I colored underneath it, that rectangle would have the same area as the triangle. Who sees that? Right? You can see it because this triangle would fit right in there. That's one way to see it. Okay? By the way, this green line would be what is called the average value of g of x. If you have a linear function, then the average value is going to be halfway in between, well, g of a and g of b. You guys follow that? What about a function like this? Well, now it's not so easy. But there has to be some average value. There has to be some place where, you know, you draw a straight line along here. Maybe that does it. And underneath there, I could compute the area of that rectangle, right? And if this little extra piece and that little extra piece fit right in there, then you have the same area under the rectangle as you do underneath the curve. You guys follow that? Okay, well then what we do is we would say that this is the average value of the function. Now, average. It's funny because I teach just about every math class there is offered at Lakeland. Okay? And I've taught high school, taught junior high, so I've done all kinds of stuff. There's one topic I've never had to teach before to a math class. And that, what's that? Geometry. No, I love geometry. That's my favorite. No, I mean a topic, not even just a course. And the topic is, I've never had to tell my students how to find an average. They all know. Why? Well, they do it all the time, right? So if I say, okay, your test scores, you got a 75, an 85, and a 90. I say, what's your average? They all know how to do it. Never have to show them. By the time I see them, they know how to do it. Right? Now, how many of you know how to find, say, something like an average temperature? How many have heard that expression before? Average temperature. Sure. How's that different from your average test score? Your average for the course? Yeah. There's this, a temperature is a continuous function. Like yesterday, last night, my son woke up this morning. He was freezing. He said, Dad, it's freezing outside. Can you close my windows? Well, it wasn't freezing. It was 55. I thought it was beautiful, sweet sleeping weather. But, you know, he says, oh, can you close the window? I say, sure. All right, I'll close the windows. But what was the average temperature yesterday? Take a guess. 73. How do you get that? Yeah. But what's that mean? Majority of the day it was 73. What's that? Oh, you could look at the lowest and the highest, right? And subtract them, and then or add them and divide by 2. You could find the midpoint of the lowest temperature and the highest temperature. Now, I told you the lowest temperature yesterday was 55. So if we say the average temperature is 73, that put the highest in the 90s, right? So actually what you're doing when you make that suggestion is you are giving me a kind of average. That average is called the mid-range quite often. Okay? Lowest and highest, you find the midpoint of those two. But that's not what they mean when they say average here. And actually, I just want to warn you, this is a very complicated question. People say average all the time, but they don't always tell you what kind of average they're talking about. And if you take finite math with me or if you take statistics with me, we'll spend a lot of time on this. Okay? I will tell you that the average that we're talking about here is the same kind that you do when you compute your average for a test score. It's a mean average. Okay? But like Brendan said, it's a little tricky here because you don't know what to divide by. Because you have something continuous. So what could you do? Well, we could do Laura's idea. We could say, okay, let's take two temperatures. Let's take the high temperature. Yesterday might have been 79. And let's take the low temperature, 55, and let's add them together and divide by what? Why 2? There's 2 temperatures there, right? So if we do that, we get 134 divided by 2. We get 67. I could say that's the average temperature yesterday. And then someone says, no, 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 the average temperature was warmer than that, right? Well, at nighttime it dipped pretty low, but for most of the day, wasn't the temperature in the 70s? Low 70s, right? Most of the day. And so someone might say, well, wait a minute, you don't want to do that. What you want to do is take measurements every hour. That's what they do over at Hopkins, right? And so they'll give you the picture. They're going to say, okay, it was 71, 72, 72, 74, etc. And then, yeah, at night it got down in the 50s. Okay, and you add them all up, and if you did it every hour, what would you divide by? 24. And maybe this gives you an average of 71.2. Okay. Same day, different number, right? Now, is that good enough? How could you get a more accurate average? What's that? Yeah, do it every minute. Of course, then you get, what if I want more accurate than that? Do it every second, right? Well, that's ridiculous. You can't. You don't have time to calculate it, right? What if you were going to do it continuously? How would that work? Yeah, question, Mike?
You take, like, half the change in Y, or do you change in X? You see what I'm saying?
No, I don't see what you're saying. Tell me.
The distance, how much that trend line changes from top to bottom,
Uh-huh.
and related to X, how much X changes.
So you want to look at this change right in here. Is that what you're saying? And yeah, related to, well, how do you want to relate it? I guess that's the question. See, here's what I want to do. I want to mimic these calculations here, because those are averages that I understand. But what I want to do is, instead of just adding 2 of the points, like this one plus that one, the high and the low, or instead of just adding 12 of the points, oh, by the way, you know, or 24. When you start doing 24 points, suppose this is temperature instead of speed. And when you start looking at those temperatures, all of a sudden, doesn't this look a lot like one of the problems on our exam? You're taking the curve and dividing it into what? Rectangles. And we're computing the area of the rectangles. So there's something going on here. Okay? So let's see if I can explain it. Now can you draw a rectangle with the same area? Well, okay. We said that the picture for this thing is you have A, and you have B, and you have some function, right? And we know that this integral, you can turn it, it represents the area of the green. But somehow there's going to be a place where you could draw a blue line, And underneath the blue line, you get a rectangle with the same area. Now let me ask this. What's the area of this blue rectangle? Well, it's length times width, right? Do we know how long or how wide it is? What do we know, Norman?
Well, if it's on like a graph, you can tell.
Yeah. So like in this picture, what is it that you know?
What would be like from A to B and then whatever.
Yeah.
The y coordinates.
So how long is that? Well, I guess it's b minus a, right? Whatever those numbers are, that's how long it is. And then this height, this is what I'm calling the average value. So I guess what I have is average value times b minus a equals the integral. Right? That's what I have. Does the picture make sense? Length times width is the same as the integral. So what that means is if you want a formula for average value, what do? You divide by b minus a. Or another way to say it is 1 over b minus a times the integral. So that is a formula that's very important. It says that the integral is going to give you the average value of the function if you just divide by whatever b minus a is. So here it is. Here's our application of average value. 6 billion people, I'm saying, is the world population. And in t years, I'm assuming that the world population is growing at a 2% growth rate. Now, where the heck did I get that from? Well, I don't know. Okay, let's just leave the source out of here. And, where did I get this from? Don't worry about that right now. Let's assume we can get better information with more reliable sources. The point is, can you answer a question like this? What will be the average world population? You can never get the actual world population. It's always changing, right? Births and deaths happen every second. Okay? We know there's going to be more people in 20 years, or at least we predict that, right? That's what this is saying, is that the world population is growing exponentially at a 2% growth rate. What does that mean, by the way? Well, maybe I could show you. Let's see if this makes sense. So I'm going to call, see, I'm using t years, right? So I'm going to make up a function, p of t. That'll be my population. Okay. P of t is going to be the population. And now I'm going to write something down and see if this makes sense to you guys. What's that mean? That's what it says. Derivative of the population with respect to time. What's it mean? Go ahead, Lauren. It's a rate of the growth, right? That's the growth. If there's a 2% growth rate, what that means is that somehow this is related to 0.02. 0.02 times what? Well, let's see. I guess at the beginning it would be 6 billion, but that's going to change then, right? How about I do this? How about I put a p there? What's this say? This says the population is, does it say growing or declining, the way I wrote this? It's growing because this says the slope of the tangent is positive. The population is growing. How much? Well, 2% times whatever the population is, that's the new population. Do you guys understand? Okay? There's a differential equation. Yeah, so why does it say exponentially? Well, okay, yeah, you're right. This is tricky. So let me show you. Okay, because this is something you guys just learned how to do, is to solve these guys. Right? How do I solve it? Well, yeah, take the antiderivative with respect to t is nice, but the problem is, do you notice there's a p over here? See, this is what you call a differential equation, right? It's separable. I'd like to bring that p over there and bring the dt up there. How's that look? Is that okay? Now integrate both sides. And over here I get the natural log of the absolute value of p. I probably don't need the absolute value because population's always positive. At least we hope so. All right? And then on this side I get 0.02 what? T plus c. Right? And moving up here, I could say that P equals what? What do I do now? How do you get P by itself? E to the 0.02 T plus C. And what's the standard trick? Separate that, because that's e to the 0.2 t e to the c. And what's this? That's a constant. So I'll call it big C. And so I get big C e to the 0.02 t. And some of you are happy about your take-home exam now because you're saying, oh, I can do that. Okay, so that's the idea. And so now, why does it say grow exponentially? Because, look, there's your exponential function, and there's your growth rate. It's sitting right there. Now, in high school, they may have just said, look, that's the function for exponential growth. They didn't show you why. Now you see why. Because this is what they mean. Okay? Now, let's use this function. P equals C e to the 0.02. Oh, there's one more thing I can do with that. Well, here, I'll do it here. We have P of t is C e to the 0.02 t. And I know that the current world population is 6 times 10 to the 9th. So the current world population, I guess what I would call that's an initial value. Right? What does the initial value usually let you find then? Lets me find what? The constant, yeah. The constant, which in this case we're calling big C. So how do I do it? Well, what am I going to put in for t? I guess, yeah, because the current world population, that's t equals 0. So when t equals 0, that's C times e to the 0. That equals, well, 6 times 10 to the 9th. So that's my, and e to the 0, of course, is 1. So I get C is that. And so my function then is P of t equals, I guess it's 6 times 10 to the 9th times e to the 0.02 t. Guys with me? Now your book will make these problems easier than what I just did. Your book will give you a function and say, okay, here's the population equation. Find the average world population. I just wanted to do this to tie in what we just learned. Okay? So once you have the function, how do you find the average population? This is the population function. What's the graph look like? Well, it's growing exponentially. Somewhere there's a rectangle we could draw over the 20 years, from 0 to 20, so that the rectangle would have the same area as the stuff under the curve. Right? That's the game. So how do I find it? Well, the average population we're going to use our formula 1 over b minus a integral from a to b p of t dt. That's the formula for an average value. And now you just have to know what to put where. So give me something we know. So that's one thing, is that we know a and b from 0 to 20. So this is going to be 1 over 20 minus 0, integral 0 to 20. And then we have p of t right here, so we may as well put that in. 6 times 10 to the 9th, e to the 0.02 t dt. So that's a constant there. That's 6 times 10 to the 9th. I'll take out the 6 billion over 20. And when you integrate e to the 0.02 t, what do you get? Well, you get e to the 0.02 t. But what else do you have to put out front? Well, I need to either multiply or divide. I've got to figure out which. Right? Because when I take the antiderivative, it has to work so that when I take the derivative, I get back what I started with. But right now, I wouldn't, because there's the chain rule. So I'd be multiplying by an extra 0.02. So out here, I'll divide by an extra 0.02. Is that okay? Well, because it's not just e to the t. It's e to the 0.02 t. Right? So I'm claiming I need to put an extra 0.02 here. You guys have to see why. Do you see it? How do you check the answer when you integrate? What do you do? Okay, let's take the derivative of e to the 0.02 t. Well, that's e to the 0.02 t bong times what? 0.02. See that? So if you know this, then when you take the antiderivative, you better divide by the 0.02 so that this guy will cancel out with that guy. Is that okay? All right. So we're almost done. We just have to work out what this is. I guess I want a calculator at this point. So let me get out the calculator. Okay, so what are we going to do? We're going to do, let's see, 6 times 10 to the 9th divided by 20. There we go. And now I'll divide by 0.02. Okay, so it's 1.5 times 10 to the 10th. And then I'm going to multiply what happens when I put in a 20 and what happens when I put in a 0. So times, so e to the 20th, oh no, 20 times 0.02, right? Minus, and then I have to put in what? 0, so I'll just subtract 1. That's what I'd get when I subtract 1. So there we go. So what's population? Guess I could put in commas here. There, there, there. So it's about 7.4 billion, approximately. So in 20 years, that's the average population. That doesn't tell you what? Okay, a couple things. Yeah, it doesn't tell you what the population is going to be in 20 years. You could get that. It doesn't tell you the total population. Actually, to get the total population, That's the average population. I guess that's the best way to say it. That's the average population. So any questions on that? Yes?
So that's not the population in 20 years?
No.
No.
So we should show you how to find that. So how would we find the population in 20 years? So we would, I guess what we would need to do is just do P. Oh, wrong P. We would need to do big P of 20. See, I have to think for a minute. Yeah, forget P. Forget this big P stuff. Yeah, P of 20 would do it. Matter of fact, let's compute that. Let's compute P of 20 and see how they compare. Let's get the calculator out. And let's compute P of 20. So what would it be? I guess it would be, where is my P of t? There it is. So 6 times 10 to the 9th, and then times e to the 0.02 times 20. So that function. Okay. See that? So in 20 years, this says that the population is going to be, well, if you put your commas in the right place, 8.9, almost 9 billion in 20 years. And that's realistic. Does that make sense? So to be an annuity, you want a sequence of equal payments into an account. How many of you make payments on something? On what? Nick? On car insurance, right? Okay. What else do you make payments on? How about on a car? You might make payments on a car. Do they charge interest on that when you want to make payments on a car? Absolutely, right? They'll charge you interest. That's an example of an annuity. How many years do you have to pay off the car? 3 to 5 years, right? And you pay every month the same amount. Okay. When you buy a house, that's an annuity. How long do they give you to pay off your house now? It could be 30 years. You could get a 30-year mortgage, and you pay the same amount every month. If you want to retire someday, you set up a retirement fund, but here's where it helps you now. You put aside the same amount every month, and so it's going into an account, right? Equal payments, equal time intervals. It's something very common in finance. Okay? Now, calculations involving annuities take some effort. Why? Because you have to figure out interest on the new amount each month, and you need to divide by the number of payments you make per year. And if you take finite math with me, we're going to spend time doing this. Okay? We'll spend a lot of time on this. Now, you get formulas like this guy. This tells you the amount in an annuity. What's that sigma mean? Sum. I equals 1 to, well, here n is the number of payments you make total. So if you have a house you're talking about, 30 years, and you pay monthly, 30 times 12, so 360, it gets pretty complicated. Okay? But fortunately for us, a nice approximation is given by this. PERT. That's one of my favorite finance formulas. A equals PERT. And this I will not do much of in finite math because you need calculus to get there. Now how do you get there? Well, 2 ways to get here. How do you get that formula? Well, either you do a differential equation, kind of like we did with the population problem. We turned a differential equation into a regular equation involving exponential growth, right? Or Another way to do it is you use the fact that the limit as n goes to infinity of 1 plus 1 over n to the n, that's e. And this formula here kind of turns into this, in a sense. It's very vague and kind of magical, but if you believe that, then you have a real nice formula. And this is used all the time in finance because it's so much easier to work with. You want a quick approximation to a problem? Use this formula. So as an example, take the last problem in the section that we're working on, problem 54. So what page is this on? Let's see. Here we go, page 518. So I guess I'd have you read it to yourself so you kind of understand what's going on. So how do I use it? Well, what are we trying to find in this problem? So in 18 years, yeah. So here's what you want to find this, right? How much is in the account in 18 years? We're going to deposit $100 a month. We're going to earn 5% interest. How much is in the account in 18 years? By the way, if there was no interest, how much would you make? Well, it'd be 18 times what? 100 times 12, right? That would be the simple answer without any interest. Now, what some people would do is just take 5% of that, and that'd be what you call simple interest. But that's way off, okay? Compound interest gets you a lot more. So the nice, easy answer, I guess, is that the amount will be approximately the following. Take PERT, P e to the RT, and do what to it? Well, this is the rate of change, if you want. Okay? And integrate it from what to what? Well, let's go from 0 to 18. Okay? There was nothing in the account at the beginning. But I'm going to integrate this. Something's weird here. So if I do that, let's see what happens. So what do I mean by P? I guess that P is not really what I want to say. I want to say payment here. Okay? So my payment is $100 per month. That's a constant. We're always putting in $100 per month. But then there's this growth here. Right? So I need to integrate from 0 to 18 e to the, now what's my r? Well, I guess I'll go 0.05 t dt. Oh, one slight problem here. This is what's called annual interest. Okay, and I have a problem here. Annual means what's the units? T is in what? T is in years, okay? And 0 and 18 are in years. So I guess I'm okay. If they gave you something like, monthly or something, then you got to watch. Everything has to be the same units. But if you work this out, let's see, we get, well, I'll tell you what, let's use a calculator. It'll be a little easier. So here I'm going to go to my y equals screen. And I'm going to type in 100, which was my payment, times e to the 0.05 t, well, x in this case. Okay? And if I just do a standard graph, there's no way I'm going to see it. So I need to change my window. Well, I'm going to go up to 20, and I still won't see it. I just changed the x's. But what I'll be able to do now is get the integral from 0 to 18. So I'm going to do second calculate. Choice 7 is my integral from 0 to 18. And it'll tell me, okay, so how much is in the account after 18 years? 29.19 it says. Whereas if I just did the 18 times 12 times 100, let's see what that would have given me to compare. Uh-oh. What's wrong here? On here. So I want to start now with, again, addressing the definite integral in finance. So this is section 7.1. And so I mentioned that this is your formula that's used for compound interest. You don't need to write that down. You don't need to know that. Unless you're taking finite math, then we use that inside out. And the reason is, for this class, we have a huge advantage, which is we've done calculus. I like to describe finite math as all the mathematics you could possibly learn in college without any trigonometry or calculus. It's a great course. It's fun because we really do a wide variety of things. But 1 2-week stint, because I know who most of my students are in there, we spend time on the business applications. And actually, this helps anybody because we're all consumers. So we'll talk about home mortgages, we'll talk about car loans, and we'll talk about annuities of various kinds. And I mentioned last time what an annuity is. So I want to get to that. Thank you. But this is your compound interest formula. What we can do instead is we can use this very simple formula, A equals PERT. So what's this say? This is the amount, say, in an account. What's P? Principal. That's the amount you start with in the account, let's say. We know what E is, or do we? Well, we've been working with it all semester. What is E? So E, yeah, is approximately 2.71. Okay? And I think I told you this. Right? It's a huge tug of war. Do you guys remember me talking about that or no? No. Okay. So let's talk about what this limit is here. See, this is 1 plus 1 over n to the n, right? All right. So what happens as n gets big? Well, first of all, guys, what happens to this fraction right here when n gets big? 1 over n. It goes to 0. So basically, this is 1 plus something about 0, right? 1 plus 0 is 1. What's 1 to any power? 1. So some people are going to say that limit is 1. But there's another argument. The other argument is this number in parentheses, isn't it bigger than 1? Yeah. And if you take a number bigger than 1 and multiply it by itself over and over and over again forever, you know what happens? It goes to infinity. So some people say this limit would equal infinity. And I could understand their argument. So you have this argument. Does it equal 1 or does it equal infinity? It's this huge tug of war. And the amazing answer is, well, no, it equals E. The limit ends up being 2.71, which I think is beautiful and mysterious. And you could actually use this as your definition of E if you want. Now, how it's traditionally done is first you study logarithms, and you study the natural log, which is what? Here, let's let you guys. Come on, we know our song. Just hum it. All right. Yeah, we know that. We're not going to that now. Okay. But that's what E is, right? E is the base of the natural logarithm. Okay. The point is that we're going to use this instead. It's so much easier. What's it easier for? Well, let me show you. So we mentioned last time an annuity, right? And when you work with annuities, I said it takes some effort. Now let me show you why. Okay. Yeah. Okay. So let's imagine you put, what was the problem we had last time? You put $100 into an account every month, wasn't it? Something like that?
Yeah.
Okay. Okay. 5% interest, 18 years, we want to see how much money we have, right? We're going to have a lot of money, right? Because remember, we just did the math last time. We said, well, let's suppose there's no interest at all. If you could save $100 a month and put it away, more power to you. That's fantastic because you're going to have 100 times 12 for the first year times 18. What's that equal? Oh, 225 minus 9 is 216. Is it 21,600 maybe?
Yes.
Okay, so that's not a lot of money, is it? I mean, I'll take $21,000, but if I have to wait 18 years for it, it doesn't seem like that much money. Fortunately, there's interest, and the interest compounds, right? And we may be surprised later how much we actually get from this. Okay? And by the way, how does it work? Well, one way to think of this is 12 times 18 is 216. Think of it as 216 separate problems. What do I mean by that? Well, which money's going to earn the most interest? The first what? The first payment's going to earn the most interest, right? Now the next payment is going to earn almost that much interest minus a month. And you guys, if you looked in the book, they had a picture kind of like this, right? And the next one is going to earn minus 2 months, right? Etc. Of course, I guess there's your final payment of $100, you know, when the kid's 17 and 11, 12 years old, right? You put in that last $100, and it only earns 1 month interest, right? But you could do this, and there would be 216 separate, if you want, rectangles. Now, get a different color here. How do we figure out, let's just do one problem at a time. How do we figure out how much interest this $100 earned? Well, you can do it the hard way, which was this guy. But since we're in calculus, let's do it the easy way. Let's approximate it with this, right? So we're going to do, you know, A equals P e to the r t right there, where my t is going to be, well, 18 years. Now, this one, t is smaller. It's a different problem, right? You won't have quite as much time with that. And for this very last one, I guess t is 1 month. So I'll have to decide, am I going to work in months or years? That's one decision I'll have to make. Okay? You guys follow what's going on? So all you do is you add all that up. But there's a better way. Instead of adding up all these rectangles, any idea what I might do?
Find the average.
What do you mean?
It's like if you find the middle one, you like kind of scale.
That might work. If I knew that these were linear in a sense, if I knew that the steps went down evenly every time, I would do exactly what you did. I would take the middle, and then I would average it. Yeah. That'd be a nice way to do it. Do you guys think that these steps go down evenly? Why do you say no, Heather? Do you have a reason, or is it an intuition? See, I'd really like to know, how tall are these rectangles? Well, I guess I do know. I have a formula. What's the formula I'm using? Bless you. Pert. They don't make that shampoo anymore, do they? No, I'm dating myself. They used to have a famous, when I was your age, they had shampoo called Pert. Look what it does to your hair, so don't use it. No, but, so yeah, we have this Pert formula, P-E to the R-T. Isn't P the same every time? Each one of these problems is $100. Isn't R the same every time? What's the only thing that's changing here? The time is changing for each person. So you could think of this as A is a function of time, P-E to the R-T, right? And if A is a function of time that looks like this, we can graph it. Now, if you graph it, I guess the thing that's changing is T. What do exponential functions look like? It turns out you can graph this as kind of an exponential function, where this exponential function will go through each of the points of the rectangle, and all of a sudden that looks a lot like what we did on the first exam. But it's backwards. On the first exam, we had a curve. We wanted to find the area under the curve, right? We approximated it with rectangles. This is backwards. We want to know what all the rectangles are. So the idea, which I think is very creative, is let's approximate that rectangle sum by an integral. Because calculus is easy, especially when you're working with E. What's the nice thing about integrating E? What do you get back? E. Isn't that beautiful? So that's the idea behind the problem. And I was jumping right to the hardest problem in the section. I thought I'll just show you that, then you can do any of them. And I totally butchered it last time. But now what we're going to do, since we've seen how the annuity works and what the idea is we're going to go back to it. And I think we'll be okay now. All right? So let's see. What problem was it? It was 54. Here were the basic facts for problem 54. And the question is, how much will be in the account after 18 years? Right? Okay, so again, let me draw that same picture I had. This one, I'm going to have $100, right, times E to the 0.05. Oh, see, now I have a decision to make. You guys want to work in years or months? I'm looking at that $100 per month, right? We want to work in months. So what you have to do is you have to adjust the interest. This is the annual rate. So what I'm going to do is I'm going to say R is 0.05, and you know how I'm going to adjust it? I'm going to divide by 12, because the interest you earn on it, that you earn on it per month, you have to divide by 12. They don't give you the full 5% in 1 month. It's a yearly rate. Okay, so 0.05 over 12, e to that. And now what about the time? Well, I have to be careful here, I guess. How many months are going to go by for this problem? What'd you get? 216, because that's 18 times 12 is 216. Yeah, so that'll be 216. So that's how much is going to be in the very first rectangle. In the second rectangle, how much is going to be here? 100 e to the 0.05 over 12 times what? 215. Why 215? Yeah, you don't earn it for that first month anymore, do you? The next one. Well, etc., right? The last one would be 100 e to the 0.05 over 12 times 1. Now, if you could add all these up, that's the exact amount, right? And we have software that'll do that. Actually, I'll show you. On your calculator, you have software that does that and adds it all up. But what the book says is, look, in economics, a lot of times what we do is we just use continuous compound interest. And so if we're doing that, then we can actually approximate this big sum by an integral. And let's do that. Let's take this sum and instead integrate the following. So instead of adding, to find the sum S, we approximate and let me write it down in black here so you have it. Now, here's the formula they give you. Let's see if it makes sense. S equals, we're going to integrate. I'll explain from what to what in a minute. It's going to be dt. Okay? What is it we're going to integrate? We're going to integrate our formula, right? So we're integrating, the thing we're adding is 100 e, is this okay so far? To the 0.05 over 12. And now maybe the trickiest part is right here. What goes there? Well, I'd like to put t, but that doesn't quite do it. Because, guys, what does the graph of e to the t look like? Well, it looks like that, right? Is that what my graph looks like? No, as a matter of fact, it does look like an exponential function, but it looks like a negative exponential function. And when I write this down, it may make some sense to you. What I'm going to put here is I'm going to put 216 minus t. Now we'll see if that makes sense or not. See, what I'm going to do is I'm going to draw the curve that goes through all of the left endpoints of the intervals. I'm drawing the curve that goes through there. You guys follow that? And so I say, what's the height of this first rectangle? Well, it was 100 times 0.05 over 12 times 216, right? And the last one is just times 1. Okay? So these points work out correctly. So when I say 216 minus t, notice for the first rectangle, I want the answer to be 216, right? So what I'm going to do is I'm going to integrate from 0, that's times 0, let's say. So then I'll have 216 at the beginning. All the way to what? Yeah, I guess to 215. Of course, it's funny because in our book we're going to put 216. So I have to think of why for a minute. Yeah, so the reason it's 216 that I put here and not 215 is because the way I'm going to add up all these rectangles is I'm going to instead integrate here, this shape. And it's going to be a pretty good approximation. It's going to be a little less than the actual value. You see I'm going to be missing a little bit, right? But if I only went to 215, I'd be stopping my integral right here, and I would miss an awfully big chunk. Does that make sense? You could see from the picture that I want to go out all the way to 216 because that's how many rectangles there are. I don't want to stop at 215. Does that make sense? Okay. So there it is. Your book, by the way, is going to call this guy here, big T, capital T. T is, the number of rectangles if you want. Big T is the number of rectangles. They don't ever say what it is, but that's really what it is. The number of payments. In my finite math class, we call it K. So the number of payments you make in an annuity.
Didn't they just call it N when we printed?
You're right. They called it N also. I think he didn't want to use N. I'm not going to say why. I don't know. This is the formula he used. And I have to point out, this is approximate. Okay? So I guess we should work it out and see what happens. So we'll pull out the calculator. Let's do that. All right, so let's type this all in. So let's see, we'll go second calculate. Oh no, what do we want to do? Just go to y equals screen. And let's type in the function. So we have 100 times second function e to the x, and then I'll put my 0.05 divided by 12. That's my rate. And now, okay, you're going to need another parentheses here. I'm going to hit times, open parentheses again, and put 216 minus x. So all of that, see, I have two sets of parentheses because all of that is supposed to be the exponent of e. It's a little complicated to put it in your calculator. And when I go to my window, well, x min, I could start somewhere around 0, and x max, let's say 220. I mean, 216 is what I really need. I'll put a mark every 100. And then y min and y max. Let's see, how much money are we expecting? Well, I guess I could calculate this to say what the first one's going to get me, right? So what do you think that $100 is going to turn into over time? How much? 30,000? All right, I'll do it. I don't know. So you think that very first $100 is going to give me 30,000 in 18 years? And I'll put 10,000. We'll see. We'll see how good the graph is. Ready? Here it is. Can't even see it. Just for kicks, let me change the window. Instead of 30,000, let me make it 3,000. And let's graph it now and see if we can see it. Okay, so now I can see it. But the first $100 does not give me 3,000. Okay? The first $100, how much does it give me? Well, that much. So a few hundred. So I'll tell you what, I'll change my window one more time. Let's make y max 500. And let's make the y scale 100. And let's graph. There it is. Okay. Yes? Yeah, I told you this is hard to type into your calculator. Okay? So I will look at it separately. But let me don't worry for now. I can look at it in a sec. For now, just let's see if we understand it. You guys see the curve? We're going to integrate it. From what to what? From 0, I said 1, I don't want 1. 0, upper limit 216, right? So that's the area, and so it says 35,000, what was it? I missed it. 30? And $30. Compared to how much? 21,000? So $14,000 just from your interest. I'll take that, huh? Now that's approximate. That's an underestimate. How much is it exactly? Well, I mentioned your calculator can do this. So you guys should know about this if you haven't seen it before. If you guys hit the apps key, application, The coolest application that these calculators come with is the finance one. It's actually the only one I have installed right now. You may have more. How many have this? Click on it. Click enter. And the coolest in the finance is this very first one, TVM Solver. Enter. Okay? And actually, this is interesting because remember Nick said we should call it N? That's what the TVM Solver calls it. How many rectangles do we have? How many payments are we going to make? Well, 216. That's going to be N for me. Interest percentage. What's our percentage? Yeah, but you can enter it as a percentage in this particular solver. I%, just put 5. 5%. Now here's some things I don't know if you know what they mean. PV, present value. Don't do anything with that yet. PMT, payment. That's what we do know. What's our payment? 100.
Why do we change interest?
Because it says interest percent. I just know that this software, you put it in as a number.
Like, why don't we do it monthly, though?
Yeah, what I'm saying.
Oh, good question. Good question. This calculator is going to take care of it for you right here where it says P per Y. That's payments per year. And so I'm going to put how many payments per year? 12. So it'll divide automatically. And notice down below, then it changes C per Y to how many times do we compound per year? 12. Okay? It's not going to be continuous interest, so it should give me a slightly different answer. So the funny thing is you can't change this. I've tried. Let me change it to 5 and go up. Oh, well, let me try it. Maybe you can. Put in E. Good question. I don't know. I'm going to leave it as 12 because I want to know the exact value. Okay? I'm assuming it's compounded monthly. And future values here, right? So I'm going to go ahead and put my cursor there because I want to know how much am I going to have in the future. The future value is not going to be 0. And watch how you do this now. Down here on the Enter key, do you see the green written above it, what it says on your calculator? Solve. This is a program that does solving. So what you do now is the thing you want to solve for, you hit the alpha key and press Enter, and that'll solve for that variable. We're going to solve for the future value. And notice it says 34,920. Well, two questions. One is, why is it negative? And that answer I know is because the way the software is written, you have to do this. You have to put the payments in negative. It has to do with the way they programmed it. Because they were thinking of it not as you're saving money, but as you're making payments, say, on a loan or something. Okay?
So,
And I could alpha solve here, and I think that'll fix that. Yeah, there it's positive now. You said Excel's that way too? I guess the question I have is, why is it lower when I thought it would be bigger?
Because the payment's at the end of the month instead of the beginning of the month.
That could be why.
Because like at the bottom, it's like which one.
Oh, did I? Oh, I missed that. Let's look. Oh, yeah, payments at the end of the month. Now, let's do payments at the beginning of the month, because on the picture, that's where my payments are. Right? And let's try it again, see if it makes a difference. Nice, Norm. 35065, okay. But interestingly enough, end of the month or beginning of the month is just the two kinds of rectangles we've studied in a sense. Okay, so that's...
Is that more than what we estimated last
It's only $35 more.
Wow.
So you can see my estimate's pretty good. And integrating this is not bad. Actually, if you're going to integrate by hand, can you do it? Ravinder says no. Sure you can.
Do it, but it's like wrong.
Well, what would you do when you say you can do it? What would you have to do?
Distribute that 25 out of 12 into that.
Oh, no. Don't mess with that. Because, here, remember, that's just a constant. Pretend it's 10.
Oh, it's a big C.
Yeah, think of it as big C if you want. It almost doesn't matter. The thing to integrate, the trick is that you have to do a u substitution. I mean, you could do this. You could let u equal 0.05 over 12 times, or even forget that. Let u equal just the 216 minus t. Du would then be what? Negative dt. So you're going to need a negative when you do your u substitution. Okay. I don't want to do it on the slide because I'm going to run out of room. I think I'm going to have us do it. And then we'll be done with this.